Where's the nonsense? So you just asked me, today, by the way, we're doing Soft Actor-Critic, right? It's like end of the day, so we already talked about it one time. I just wanted to have it on video from Varun got here. So Varun asked, what is the difference between value functions and Q functions? So in reinforcement learning, remember SARSA, you have states, actions, rewards. So you have a state space, you have an action space, and you have a reward space, which is usually real numbers. And you have like little s lives in the state space, so that would be a state that you might see. An action, little a would be a particular action you might choose, and little r might be a reward you actually see, like 7. Okay. So with the setup, you have like Markov decision processes, and you don't have to go into the mechanics of all that. The idea is like you pick a state, you take an action, you get a reward, and you observe a new state, and then you can do the same thing again. So that's why it's SARSA, because it's state action reward over and over and over and over and over. And then the episode ends. So what's going on is you'll have a state at time. So we'll write states with little t for subscripts sometimes. And so t is a number. And so you'll have state 1. And so your observations that you have are like state 1, action 1 is the action you choose to take. Reward 1 is the reward you received at time step 1 after taking action 1. And you'll see state 2, action 2, reward 2, state 3, and so on. Okay. So this is what the observations look like. And that's everything that happens in reinforcement. So you often want your model, your agent, to learn to predict the reward it's going to see over the rest of the episode based on how it chooses to play. So you'll have like some policy network that has weights, and it'll be like a neural network that looks at a state and tries to figure out what the action should be. So it selects actions. And then if you let that policy network play, it's going to play the game out, and it's going to collect certain rewards. So what you can do is you can say, hey, I have a particular set of parameters theta for my policy. So I'll write my policy function as pi sub theta, which means it's parameterized by the policy parameters pi. And you can imagine that I start in state 1, and this spits out a probability distribution over the action space, and I can sample action 1 from that probability distribution. So that's how it works. And then you get a reward, and then you look, and to see what your next action should be, you plug state 2 into your policy network and sample it for action 2, and so on. So that's what pi sub theta means. Now, some extra notation. People write pi star to mean the optimal policy for a given state. And that's the one that maximizes the expected reward of the whole thing. And what you can do is you can say, hey, I'm going to define this thing called return, GT. And this is going to be a sum, and it's going to be all at time step t, like if t is 1, it's going to be the reward 1 plus the reward 2 plus 3. And it's going to be all the rewards you're going to get over the rest of the episode, assuming you play the same way with the same policy. So the way you write this is tau greater than or equal to t, r tau. So G1 is R1 plus R2, so on. G2 is R2 plus R3, so on, and so on. So what you're trying to do with a value function is, given a particular policy, the policy you've been playing with lately, you want to predict your returns, given the current state. So what we're saying is the value, according to the policy pi sub theta, is a function of a state at time t, and it is trying to approximate gt. The rewards you can expect to see over the rest of the thing, over the rest of the episode. And of course, and this is sampled from pi theta, which means that this is gotten by playing according to that. Now, there's also an optimal value function, which is assuming you play perfectly. So it's b star at st is equal to, it is actually equal to gt, assuming that the returns are sampled from playing according to the optimal thing. But this is not exactly true. It should be the expectation. So in fact, this should be an expectation. But it's only approximate. Okay. But this one's equal, it's not an approximation. Value function is exactly correct. Okay, so that's value function. So it's, you look at a state and you get an expected reward or return.
For this optimal one, you have to estimate, right? Approximate.
No, for this, if you even want to talk about b being an optimal value function, b star, it has to be exactly right. Otherwise, it's an approximate optimal value function. So the notation is b star corresponds exactly to the expectation according to pi star. But this one doesn't.
I mean, yeah, that's like in practice, you have to approximate it, right? Or can you find it out?
No, you don't approximate it. If you are capable of talking about the optimal policy, there's restricted cases where it would be true, but the cases where you're usually talking about optimal value are in the case of dynamic programming problems, where you have a completely exhaustible search space for the policy. And so you can look at the total game tree, and you can actually compute the value function through value iteration and open converge really quickly. So this you actually compute exactly most of the time. If you're going to talk about this, you probably don't have to approximate. The value function eats a state and spits out an expected reward. Q function is almost exactly the same thing. Q for a particular policy is a function of a state at a time t and an action at a time t. And it is meant to approximate it's meant to approximate, let's see. What is the expected reward for the next step? So the expectation according to choosing action A at time t of reward at time t. Plus some value function of s t plus 1. And s t plus 1 is sampled from AT. And really, I could take this.
So you're taking expectation on the current reward plus the value function's output of the current state.
Yes. But when you compute a Q function, you don't actually have also have a value function. It's just in the theoretical limit where you are able to train forever and get these things to be perfect. This thing is supposed to be approximating something of this form. So here's why this is done.
It's just to think about it?
Yes. Yes. In practice, this just happens to be a neural network. It spits out here. And this is also a neural network, but you don't have to have a neural network for your value function to get a Q function. So you just won't learn a Q function by itself. So what the reason for the difference is this thing. Look at these two in comparison. You plug in an action here, and you didn't here. But they both output the same thing. It's expected right now for this time, what can I expect the total return over the course of the episode to be? The difference is the action. So with this, you will only play according to pi theta. With this, you'll make the first action be AT, whatever you plug in to the Q function. The rest will be pi theta after the first step.
Do you concatenate them and give it into a neural network, or how does he architecture?
You literally just plug in the current state, the current choice of potential action, and then the neural network spits out a number for the expected return.
I mean, they are concatenated to form an input vector, though, right?
Yeah, for the neural network, that's right. Yeah, roughly. Yeah, so the idea is like with this, when you're learning with value functions, what you do is you say, hey, I have a model of the game I'm playing, and I'm going to look at I'm going to figure out what my next move should be. So I'm going to plug in my current state. Well, that's not going to quite work because it doesn't tell me anything. It just tells me how can I expect it to play. So what you do is you say, imagine all the different actions you can take right now. And then imagine what the world would look like after you took those actions. And then check the value of those states, the after states of taking each action. And then pick this action that has the highest after state value. Okay. So in tic-tac-toe, you have like 9 moves you can make. Imagine you took each of those 9 and check the value of the after state. Pick the one that maximizes the value of the after state. That's value function iteration. But with Q functions, you don't even have to compute the after state. You have to know how the world works for that. You have to know how your actions correspond to changes in the world. Well, with Q functions, you just say plug in my state right now into a neural network, and then plug in all the possible actions into the neural network, and it's just going to spit out the return.
Is that all the possible
actions? Yeah. And then you choose the action that maximizes the Q function. But you don't have to compute after states in this case. Here you plug in, really you do this here in practice. But here you plug in the current state. So really they're capable of the same thing. It's just this is more used now because it is computationally expensive and you don't need a world model to understand how action is corresponding after state. That's the only difference.
Is there any case where you would not want to choose Q?
No. Wait. Can we, what about the PDO? Use value functions there?
Yeah, use value there.
I think, let's see. I think it's because we're doing full rollouts and we're not doing online learning. So online learning generally goes well with Q because you don't want to be computing after states online when you're in a game.
What would you normally do?
It's expensive. Simulated
Besides the expensive part.
That's what I'm trying to think. How does the PPO do it? It collects a bunch of episodes, runs an update step. It updates the policy based on the value function. Oh, I know why. It's because you collected your episodes with a static policy, right? In PPO. And so you only have, you're never really considering alternative actions in PPO.
Yeah, so For one loop, yeah.
For a batch even. Yeah, for one state, you never consider alternative actions because you're running them through a policy network to get the next state, or to get the action that you want to take, then you get the next state.
Yeah.
But because you saved everything and you can't consider alternatives, it's like that it's conceivable you can design a system that does the updates using alternative actions and thinks about what you can done instead. Right. And in fact, Actor-Critic, the Soft Actor-Critic does use a Q function. But just because of optimality, because in PPO you're assuming you can run trials really fast and you can actually try other things instead of just considering what you think they might result in. Typically when you use PPO, you're going to be doing that because you're not saving a replay buffer for like dreaming or whatever. So it is faster, and so PPO is trying to like maximize speed of collecting more experience and running through more episodes. And so just end up using this because it's on policy.
Yeah, so it is literally like trying to learn the environment itself versus that is like trying to learn the actions more. I mean,
yeah, I would say the main distinction is this tends to correspond to on-policy training. This tends to correspond to off-policy training because you're allowed to consider actions you didn't actually take. Because if you're doing off policy, then the actions that you actually took may not be things that your policy network would decide to choose now. And the value function corresponds to whatever your policy can choose now. And so you really want to consider things you chose in the past that you wouldn't choose now, and you want to update on those. So you need Q function in the case of Soft Actor-Critic because it's all policy. This training update you collected 10 years ago. You wouldn't choose those actions anymore. So it doesn't even make sense to use the value function there.
I mean, it depends on the buffer. Like you can.
It won't work at all. You can't use this as a C. You could probably use this in PPO, okay. But it's just faster.
Has anyone tried that?
I don't know. I think maybe DQNs. No, DQNs have a replay buffer. I think anytime someone uses a Q value or a Q function, it's cheap enough to do replay buffers that they do off policy anyway. So I don't think anybody does like on policy Q functions.
So here, are you not, so in the Q1, so in soft policy, soft actor-critic, are you not running episodes before, like at the start of every training loop?
No, you will actually do your updates during episodes.
Yeah,
you can learn. You can actually learn perfect performance from zero experience to that single episode. All right. So that's satisfactory, kind of.
Yeah.
You can plug an action into the Q function.
Yeah. And it is on policy.
Right. Okay. All right. So the way Actor-Critic works, or Soft Actor-Critic, is Actor-Critic is you've got an actor, which is a policy network. You've got a critic, which is a value network or a Q network that is looking at the actor and trying to give it like some kind of feedback on whether his actions are good or not. That's true. And it may also critique past actions to give continued updates on things where it could improve from past experience. So in Soft Actor-Critic, you have this funny setup where you have one policy network and you've got 4 Q networks. And like it's set up like up here. So these two kind of go together. And this one kind of trains really slow. This one trains pretty fast. But this one is like a target. So this one updates in the direction of this. Excuse me. This one updates in the direction of this, but it's slow. So this one leads, and this one kind of trails behind in a lagging way. And same way with this one updates slow and trails this one. And these two compete with each other to not get too excited. So they'll like predict that there's going to be huge rewards from changing the policy really fast. And then the other one might be pessimistic. Like Q1 might be too optimistic and Q2 is kind of pessimistic. The algorithm is going to choose to go with Q2 because it thinks that, getting too excited about the rewards that are possible is probably not accurate most of the time. Instead, you should just train for longer to make sure that your updates are not jumping out with weird policies. So that's what the setup is. So you start by initializing your your 3 policies for your 3 parameter sets for policy, Q1, and Q2. Xavier initialized them just randomly.
Xavier is, what was Xavier?
It's like a normal distribution. And it's normalized by the size of the parameter space. The dimension of the parameter space. So then you make this replay buffer, which is like a big vector. Just contains a bunch of stuff. It's a list. An array. And it's empty at the start because you haven't got any experience yet. So then you initialize your target Q functions, so the parameters for the Q networks. And you just literally set the target ones equal to the parameters for the regular ones. That's the start. All right, so that's the setup. Now, you loop till convergence, and what that means is you do this whole thing up to the end over there, over and over and over until the performance stabilizes. And then you're done, you can just run it through a wall. You don't have to train anymore. So this is what the loop is. You play in your environment, and you observe a state S. And based on state S, you take your policy network over here, and you plug S into the policy network, and you get an action distribution. You sample that action distribution, and get an action A. You execute action A in the environment, and then you're able to observe what the next state is, call it S prime, observe what the reward is, R, and observe a done signal D, which is true if the episode is over, and S prime is the terminal state, or it's false if the episode's still going and you can take more actions. If the done signal is true, so the S prime is terminal, then reset the environment state, keep training.
This done signal is coming from what again?
The environment. It just tells you if the episode's over. So like in Lunar Lander,
Got you.
right, it'll tell you if you hit the ground or if you're off screen or if the episode did nicely. So upon each one of these action executions and observations of the after state and reward, store this vector or this 5-tuple SAR S prime D in the replay buffer D. So just append it to the replay buffer. You do this every single time. Now that might grow huge in memory, so BJ and I were talking about like there's ways to choose particular states that you want to save in the replay buffer that might be like more interesting than others. And you can use like your Q networks to see whether your predictions for the reward was correct or not. And you can just do your, you can plug in, but you can use this as a metric for what the surprisal is. And it would be like Q, say V1 or something. You could also use V2, it doesn't matter. And you put in the current state, the action you did choose, and then you subtract away whatever the observation was. So it's like the reward you saw plus Q S prime, and then you would put in the policy network's choice for the next action. And like you would instead do A prime, which is sampled from that distribution. And so this will give you some kind of measure of the error in what this Q function is predicting the reward here ought to be. Because you can imagine this is approximately equal to this thing. And assuming everything goes right, what you observed that's different from what you should expect, what you observed that's different from what you're expecting is this reward. So this should be equal to that, and there's an error in this thing, so just take this minus this, and it tells you the error in the reward, and it updates this guy, and you can make, if this absolute value is huge, you can save that in your replay buffer. If it's small, you probably don't need to save it.
I see. This is what you're thinking.
Yeah. There's some measure of surprise based on the Q functions. Okay. So you store your observations in replay buffer. Now, throughout the training, you're going to do time steps. You're going to literally go over time steps and make observations every time. And you'll have some kind of frequency for when you want to do updates. You'll be storing stuff in your replay buffer, and every so often you want to do an update. So maybe every 1,000 time steps. So once it is time to update, whatever that criterion is, maybe it's once you fill up your, because if you're populating your replay buffer according to the surprisal threshold, maybe in the last 1,000 time steps you didn't get any new replay. Like new experiences in your replay buffer, so maybe you need to wait until you've added another 100 replay buffer experiences. Who knows? But whatever your criterion is for updating, do this. So when you do an update, you will do multiple update steps. So however many you want to do per update sequence, you'll call update quantity, and then you'll do this loop, this for loop, that many times. So what you do is you say, randomly sample a batch of transitions B. So these things you get added into your replay buffer are called transitions. You just sample a bunch. VJ said, how do you know what to sample? Well, it could be based on surprise or whatever. It could be uniform. Who knows? It could be based on recency.
But transitions, I see.
Just some of these guys.
Yeah.
However you sample them does matter, but they don't say how. Yeah. To do it effectively. Let's scratch this out. Okay. So
the small d here,
that's the done signal.
either 0 or 1.
0 or 1. Right. So we want to compute targets for the Q functions. So that has to do with these targets up here. So we're actually going to use the target Q networks here. So you say, all right, I want to compute this Y thing. Who knows what that is yet? We'll look and see. So you look at the reward for the current transition that you're looking at. You add that to some discount factor, gamma. So it could be like 0.99 or something, or 1 even. And then you multiply that times 1 minus D. So if D is 1, that means the episode just ended. And that means you're not going to see any more rewards. And so the total expected reward for the rest of the episode should just be the reward you saw. There's nothing else coming. So if the episode's over, you're not going to get any more later rewards. So the signal that you get, the reward signal, is just the current reward. It shouldn't be whatever you would expect to see in the future. So if D is 1, this thing is 0, so this whole thing dies into set bar. If it's 0, you get this whole thing without the 1 minus D. So you kind of think of this as whatever here. Now you look and see for 1 or for 2, so either these two guys or for these two guys, 1 or 2, you will choose whatever minimizes this expression and make that what you multiply times gamma to get your Y here, this target. So what you do is you say, hey, it's reward from right now plus some discount factor times this thing. Ignore this for now. Okay. And this is the Q value for the Q function for the next step and some action you might choose in the next step. Okay. So it's like the current reward plus the next expected reward. So it's like it's trying to say the return of the whole episode using the real life observed reward and then predicting for the rest. So it's like a return. But what you do is you update by adding, I know this is minus, but it's actually adding the entry for the action distribution for the next step. So you want to maximize that entry. So it's going to act as the direction you're going to move in your update step for your Q functions. So
and you're only updating this based off the target function, target network.
That's correct. Yeah, this number is calculated from the target parameters.
For both of them.
For one and for two, yeah. So here you're only looking at these two guys and choosing the minimum over whatever this expression is. So whichever one of these is closer to the entropy, or actually whichever one of these is smaller. Yeah, because this is a constant with respect to I. So the thing is, this alpha parameter is something you choose. It's always going to be a positive number. If it's small, you're going to favor exploitation because the entropy is not going to be there much. If it's large, you're going to favor entropy, which means your action distributions are going to need to be more uniform, so that you will be more likely to learn policies that are kind of like dropout, where it's a regularization. And it's entropy over the after state action distribution. So you're using A prime S prime.
I'm trying to draw the analogy with this and like the PPO update step.
Right. Yeah, the difference is you get this Q function.
Imagine if you're using Q function in PPO. Will this update step be exactly the same?
No, it won't have this. You don't use
Yeah, that's right.
But instead of using, like, if you ever use V phi of S, instead change this to like Q V S comma A sample from pi theta S. And then it should be approximately the same. The issue is that this is kind of decoupled from your action, your policy parameters. This is. So it doesn't have theta. So there's some decoupling that goes on where this is coupled. Doesn't affect performance much, but it's a little different. Okay, so then what is this A prime tilde? All right, so you look at the after state, you plug it into your current policy network, and just sample the action from the action distribution. The neural network spits out. Okay, so that's this, and you just minimize the Q function. Use the one that minimizes it among the targets, 1 and 2, and then this is the target Y. All right. Next, you got to update your Q functions, Q1, Q2, not the targets. Yeah. And we still haven't updated the targets, but we'll do that at the end. You update Q functions by doing one step of gradient descent. And the gradient you're going to use is this thing. Like this whole expression. So the gradient with respect to the parameters for Qi, and you're going to update both of them. So you'll do this for I equals 1 and for I equals 2. And you'll do gradient descent, so you'll get phi, this gets set to phi minus some learning rate parameter lambda times gradient with respect to phi, and then all this crap.
Yeah, it's pretty simple. I understood that.
So this is just an average over all the transitions in the batch.
Normalized version of normalized of like a mean square.
Yeah, mean square error.
Mean square error. Yes. So okay, so in grand scheme of this entire Actor-Critic stuff is like that you're having a target network that is affecting the policy parameters and a faster learning queue network that is affecting the target network.
No, it is the policy parameters are not getting updated until the end here. So we haven't even gotten to that. What's going on is you're using the target network in computing the target, which is like you make a real observation and you use the target network to predict the future step, and you add entropy to that to regularize that ignores entropy for now. This is only responsible for future stuff. It's a little more stable than the other Q network. because it's not going to be updated as fast. And then for the current Q function, not the target, excuse me, not the one used on the after state, you use the faster updating one. And you want to update the parameters for it. And so it actually has to, though. So you're using the target here for the future stuff where you're updating based on this guy. So this one just updates slower. Like it's more stable. So you want a stable basis to kind of update the directional. Kind of your baseline.
You said this one's more stable?
This one. Like the targets.
Yeah.
And kind of the intuition I have for it is like if you've got the target and you've got the current one, not the target, like Q1, then V1 is going to maybe jump. Well, no, it's like the target. Yeah, V1 is going to jump in parameters out this way somewhere, and then the target's going to move in the direction of the V1 a little bit, and this might jump over here, and this guy's going to move here. So, very jagged here, but this one's going to move. All right, so this is really easy to figure out. And then you have this update your policy by one gradient ascent step. So where I did gradient descent, you just changed to a positive instead of a negative. So to add some constant multiple of the gradient. And this is the gradient you use. You only have to do it one time instead of two times. So you're only doing a policy network. And it is the sum of the mean of this expression. And it's going to choose whatever minimizes this difference for each transition in the batch, or each state observation among transitions in the batch that you're looking at for your replay buffer. So this is just Q value at the current step minus the entropy. The reason that we have this thing, this is a little bit different from what was over here. It's not a prime tilde, it's just a tilde theta. Yeah, so it depends on theta this time. This one did 2, but this is for the current state, where this is for the new state. So what goes on here is we need to be able to differentiate this with respect to theta. Here we were using this a tilde prime. We were differentiating that with respect to phi. So it doesn't matter that this isn't differentiable with respect, to theta, because we're not even going to differentiate with respect to theta. We get a problem if we try to differentiate these actions with respect to theta, because we're doing this. Thetas are used to figure out the action probability distribution via this formula. A is sampled according to I theta something yes. And this thing is equal to this. Probability theta A1 action 1 given this. I theta A1. So the first possible action is the first possible action. And so these all add up to 1. They're all positive and 0. So what you do is you end up actually picking one of these. Like say you pick the first one and you run through the episode. Well, how do you like differentiate this expression? Or how do you differentiate a function? Because like here, we're differentiating pi sub theta with respect to theta, where we plug this in. And how do you even you could differentiate this number in this vector with respect to theta, because if you change theta, the neural network updates, and like this number is going to change by something else. So it'd be nice if we could use that. But what we do is like I think it's when you do the Q function actually, you'll have Yeah, you'll be doing chain rule. And so you end up having to actually differentiate this action that you chose, which is sampled according to this probability distribution. We can differentiate with respect to theta the components of the probability distribution. We can't differentiate with respect to theta the samples sampled from that probability distribution. This doesn't even make any sense.
You're saying you cannot differentiate the sample from this distribution with respect to theta? I mean the theta parameters?
Yeah. So if I get a neural network that spits this out and I plug in theta from my parameters, let's say I want to differentiate this component with respect to theta.
Let's say theta 1. Huh? Let's say theta 1. Or just pick theta 1.
Well, yeah, I can take a gradient. Yeah. So I can, and what that is saying if I update the parameters a little bit, let's say I got one parameter, say theta, it's just a number. Well, this will change some amount if I nudge theta in some direction.
And then you can divide them, and that will be your.
Yeah. So what happens here is over here, I want to do this gradient calculation, and actually it turns out that the actions I chose depend on theta.
Yeah.
And how do I, because I need chain rule, so I got to differentiate the actions themselves with respect to theta. Because Q is a function of the action. But the action, I only took one action. So how do I differentiate the Q function? Because I have to do chain rule and I have to differentiate the action with respect to theta. So there's some discrete thing that doesn't have any dependence on theta, really. It's like piecewise, so if I change theta a little bit, it wouldn't change the action I chose. Yeah. If I change it enough, it will. Not small enough. So I can nicely use this setup where I just differentiate the number corresponding to that action. That would be nice to use that. So they have something called the reparametrization trick that allows you to get something that's a meaningful derivative here. That's this.
This is what you were missing from the OpenAI paper?
Yes. It is. And they have an issue in the OpenAI paper where they talk about how to do this, but they only talk about it for continuous action spaces, which we don't really have in our minds. Sort of, but in the current environments, we don't, and the explanation they give for continuous action spaces makes no sense. So what you do is you say, okay, instead of thinking of this as being an action, you should set it equal to, like you're going to end up computing, so you want that derivative. So you're going to end up getting gradient with respect to theta, and then you're going to end up getting like Q B1 S A tilde T, or A tilde theta of S. Well, what is this? It's just this gradient with respect to A theta tilde S of Q V1 S A tilde S, and you could change this to say gradient with respect to the action you choose, which in discrete case doesn't make too much sense. Fine. Times, and you use chain rule and you say gradient with respect to theta of A tilde theta S. I gotta figure out what's going on with this guy though. It's a little funny. Right. Oh, and I see how it works. It'll be clear in just a second. You should keep it the other way with the tilde theta. That's. So what they do is they define this thing funny, that A tilde theta.
OpenAI?
Yeah, everybody. So the reparametrization trick is to do that. So what you do is the following.
Oh,
A tilde theta S is equal to mu theta S plus C sigma theta S. I'll explain what this is in just a second. So you plug a state into this action function thing, it's going to sample standard normal distribution to get C. Mean 0, standard deviation 1. So that's going to be a constant. And it's not going to depend on theta. So when we differentiate with respect to theta, the C is going to be constant, so we can pull it out. Now, what are mu theta and sigma theta? Well, let me get blue. Let me go over here, actually. So you're taking S and plugging it in for each of these. And so the way to define is this. Look at pi theta. And choose any action and S, and you get a probability distribution. And it's going to be a vector. First action, second action, and vector. So all these probabilities have a, they are, you can compute the mean. So this is a probability distribution. You can compute the mean of these guys, of the probabilities themselves.
Well, what sense will that number mean?
I see now. Okay, so you compute the mean for each one.
For different states?
Yeah, I think in the continuous case it makes more sense. Because you'll have like one output action, and it'll be a probability distribution of the real numbers. So I think the mean here in the discrete case is going to be a different number for each. It's just going to be whatever the I is. Because it's either 0 or 1 on you pick it or you don't. And so 0 times chance of not picking it plus 1 times the chance of picking it. It just ends up being the chance of picking it. So it's the probability of it. So mu, I think this will be mu theta S. Oh, I see. So in the discrete case, it works a little bit differently. In the continuous case, it's how I wrote it here. But in the discrete case, this is more correct. And so what you do is you say, the number these 1 through n, compute the mean among those, like the expectation. And get mu. It seems funny, right?
It seems funny. Yeah.
I'm glad you're critical, because I feel like last time I skipped over this a little bit. So explain it here. So
Just to be clear, this notation, like when you put a dot, means that you're trying to do sampling for all the possible actions given all the possibilities.
say that one more time.
When you put like a dot in front,
Yeah.
Are you doing this for a given state for
Yes.
all particular actions?
That's
You're
right.
trying to see the probabilities from them?
Yeah. So this would be
And this is for a particular net.
pi theta A1 S up through pi theta
Right.
ANS.
And you're talking on the mean of this, right?
So that's what I'm wondering. It's not clear what the mean really is. So they say in the paper, concretely, the actor network outputs a mean mu theta S and a standard deviation sigma theta S when the state S is given as input. Mu theta S and sigma theta S have the same dimension and are both vectors.
What?
Yes.
How does that make sense?
So
Oh, I mean,
for each,
mean of these numbers will be the same number.
I don't think it's a mean of these. I think the means are literally these. Feels like that.
But then how do you define the standard deviation? Like standard deviation for this.
That's right. It would be 0.
Yeah. Not 0, but like standard deviation of this list needs a mean of this list to see the deviation from, like deviation about what point. So like you have to calculate a mean of this.
Well, you have a standard deviation for distributions without taking samples. You could do it that way. You could say like, because what it is it's the chance of picking action 1, probability action 1.
Or is it that this is not for a particular state, but this is for like a bunch of states, and then you're taking mean of those vectors and
just one state. So you can do it as a Bernoulli distribution. So the probability of choosing action 1 is equal to pi sub theta of A1 given S. That's what pi theta is doing. And so the probability of not choosing it is equal to 1 minus that. So the standard deviation for this random variable is going to be so let's compute the variance. Call this x. It's up 0 or 1, which is 0 if you choose action 1. It's 1 if you 0 if you don't choose action 1. 1 if you choose action 1. The variance of x is equal to the expectation of x squared minus the expectation squared of x. And then I'll take the square root of variance to get the standard deviation. So what this ends up being is, well, the expectation is literally just what the probability is. But
of x squared.
Of x squared, so it's a little funny. So this is going to be pi theta A1 given S squared. Is that right?
Yeah, that's right.
This one's funny. You have 2 outcomes possible, so it should be a sum of 2 things. And it should be the probability of, well, it should be 0 times something, so you don't have to care about that. For the first outcome, if you don't choose something. But if you choose something, it should be 1 squared. So that's the outcome. Times the probability of getting that 1 squared.
Let's say,
so it is this. With no square on it. So the standard deviation. Greater than or squared.
In a situation when there's like 0.4 and 0.6, for example, both, like if you square those, then 0.4 squared is 0.16, and then
so probability of A is equal to 0.4, and the probability of not A is 0.6. The expectation of A, or X, or whatever you want to call it, is equal to A being 0 times the probability of not A plus 1 times the probability of A.
oh, that's right. Yeah, I was being stupid.
But when you square it, this stays 1. And this stays what it was. So it doesn't end up being squaring the whole thing.
Yeah, that's right.
But on the expectation squared, you do square the whole thing, so it makes the probability get squared. Which shrinks the number, so it keeps positive. I think this is
likely what they're talking about, but it's a question of whether that works or not. Critic, and then discrete action space. Yeah, there's an article. So they're explaining the entropy changes. That doesn't matter any. The policy network outputs a mean and a variance. Okay, I see. So we have a little bit of a weird setup here now. Okay, now I get it. Policy is not outputting this. Policy is eating a state and outputting two things, mu, theta, s, and sigma, theta, s. And what's going on is when you actually sample to get an action, so when I say like A is sampled according to pi theta, then that means A is sampled according to a normal distribution with mu theta s and sigma theta s as the parameters, where these are coming from this. So, yeah, you're picking your actions according to a normal distribution now. And it's...
And when you,
how does this work?
When you say policy is outputting these two numbers, like, is it like explicitly going through the network? Like, is there...
Wait, I don't get this still. Because how are you supposed to... Okay, how do you... You get a bunch of actions. Policy network outputs a number for each according to a normal distribution.
It has to be the other way around. If the policy network is already giving you mean and standard deviation,
maybe this is for the continuous case.
you need to have more diagrams.
Yeah. This article might say, oh, okay, so that's for the continuous case. I'm sorry. So what do they do in the discrete case?
This one's like much more,
More gotchas.
yeah, more stuff going on than pre-feel. Like
Right.
much more.
Just to get to the end, like the last step you do is you just have this linear. So you want to update your target networks, 1 and 2. So you update them by doing a linear interpolation of the target network weights and the corresponding regular Q network weights. And so this is a linear interpolation. So if it's rho being 0, you'll just get the Q network weights.
Right.
But if you have rho being 1, you'll just get the target Q network weights, so there won't be any update at all. And so you want to be close to 1 so that it's slow updates. So you pick like 0.995 is what we're selling in stable baselines. But yeah, the rest is literally just figuring out this reparametrization trick, which we thought we had. Because we thought we were taking like this thing and we were computing like a mean among probabilities or something. And taking that formula, like the mean of the probabilities plus the standard deviation of the probabilities. But that doesn't make any sense to call like some kind of action thing anymore.
Why not? Why not?
Take a bunch of probabilities, compute their mean and their standard deviation, scale the standard deviation by a random number, and add them together, and then try to think of that weird statistical combination of all these probabilities as an action itself. Don't sample it as a probability. Just think of that number that you get as
You have to
as
pick
an
one
action.
from that sample.
But you don't have a sample anymore. I mean, you don't have a distribution anymore. You just have a number. If you take all your probabilities in your action probability distribution, you mean them, you standard deviation them, you add them together, you get a number. You don't have an action distribution anymore. There's nothing to sample, you just have a number. Like, it's a meaningless statistical thing.
Why not?
It's a number. How do you sample a number?
For a mean and a standard deviation, you can think that it is a distribution. Like,
They're numbers. A mean is a number.
but if you think in for this guy's case, you can do this using noise, have a bunch of generations, and then that will be your.
But that's not what they do, though. So I gotta know what they do because it's not clear. They actually have code here, so I can check this.
What paper is it?
It's like a totally random Medium post. Yeah, the original paper on Soft Actor-Critic is not easy to read because it has continuous distributions or continuous action space, and it's not meant to teach from. It's really messy.
Does anybody have a book on this stuff? No one?
Usually what people do is just read the code. So that's what I'm taking a look at. So what do we want? We want reparametrization. So we're doing the policy update stuff. Learning and loss. The actor loss is going to be up here. Actor loss, actor loss. Okay, here they define it. Q and then alpha. Log action probabilities, okay. So get action info is what I want. Okay. And it seems like they don't even do anything like this here. They propagate the state through the actor. And they never show computing the gradients. Polyec update. Target network. Okay, maybe here. So I want the actor loss backward. Yeah, it does not say.
They're keeping us like in the dark.
Mm-hmm. It is indeed straightforward to adopt it for the discrete action setting. We know that the policy should correspond to the softmax of Q divided by alpha. What?
Why is softmax of the Q function? For continuous actions, you must sample and try to approximate this quantity. However, in the discrete setting, as you can enumerate all the actions and get their Q values, this step becomes immediate. Hence, you can get rid of the policy network.
So it looks like they don't have these. And they're just using these numbers somehow,
Which is kind of what we originally thought. Hence, you can get rid of the policy network. Second, the V value is simply a dot product between the policy and the Q values. That's true. Both are functions of the Q. Hence, you will find that V equals alpha times log sum x Q over alpha. You can use this in the TD backup, hence we can get rid of the value network as well. In the end, just stop explaining whenever I show what they actually do. You then won't be able to compute the policy grading. You don't need to change the SAC algorithm. Instead, have a softmax output layer and generate approximate samples from it using the Gumbel-softmax distribution. The difference is that the Gumbel-softmax can be sampled from with the reparametrization trick, so you can pass gradients through the samples. Still doesn't explain. Maybe here. You can write oh, I see. It's simply.
So they say we don't have to do all this funny shit in the discrete case. You want to, it's conceivable you could just take the action you actually took from your transition.
So you did that.
And just stub that in. Now, this Q is a number that depends on A. But you're fixing A, so it's fine. And you can just differentiate with respect to theta. So that all works.
Yeah.
This is problematic. It's actually fine. There's no differentiation. You just have a saved action. You just run through the policy network. You can also resample and sample again to get a given state. And if you do that, you do have a number. Let's say you pick A1 on the resample. You're ending up looking at this probability to get your sample that you did end up choosing, and you can compute the derivative of that probability, even though you picked an action, which was this one, which is like either you did or you didn't pick that. You still differentiate this probability with respect to the theta.
Monte Carlo methods, you do that. But I just cannot find what this reparametrization trick is. There's a paper on it from late last year, November, on archive. What is Gumbel-softmax? Okay, so it looks like you actually have to read about this particular softmax function. When computing the outputs for your policy network, you want probability distribution, so you need softmax, but the Gumbel-softmax is actually differentiable action after you choose a particular action. So without that, we've kind of been working in the dark. You have to have that for discrete action spaces. And there is an article that makes it very clear that I'm going to send. It's a GitHub page. Sassafras13.github.io /Gumbel-softmax. It has a lot of pictures.
That's good.
Nice big font formulas. So I'll probably have to read this over the next week or so. It's like 4 pages long. It's like it's really short. No, it's like, I mean, you can see it.
It's touchscreen.
Is your touchscreen?
Yeah, you didn't know about that?
Oh, I didn't know. But this is it. It's just.
Okay.
And short.
Okay, that's short. Yeah.
It looks like it's very elementary writing, so.
Yeah.
So, yeah, it looks like there was a problem we couldn't actually get around without reading something about Gumbel-softmax. So that's Soft Actor-Critic, and the next meeting in 2 weeks, at least by the end of it, we should be running Soft Actor-Critic in cool environments. And hopefully we'll have like some early.
Maybe you really want
Yeah, maybe. So if that gets to a reasonable level in time, we'll do that.
Do you think these AI labs don't publish like high quality stuff to like make it accessible? just because like to have the edge or something.
Yeah, you know who Dario Mode is?
Or Dario.
He's the CEO, the founder of Anthropic.
Oh yeah, yeah. David.
Yeah. So he gave an interview like yesterday or something. He's like, there's a huge national security concern where like, you know, our trade secrets in our industry are like 1 or 2 lines of code. And if, you know, foreign actors get access to those 1 or 2 lines of code, they could beat us. And so it's really important that the government like makes it safe for us to operate and really act and stuff.
Because if I spend like 1 hour on like thinking about like how to differentiate that, I think I can probably come up with something.
Yeah, if you just try like
Yeah.
crazy stuff.
Yeah.
Right.
Shouldn't be too hard.
But I mean, somebody has to tell you it's possible for you to try it, or at least it like has to be something that you arrive at wanting to do, and like have the energy to sit down and like suspend your disbelief about it being impossible for a minute. So there's a lot of stuff like that. Like with transformers, the positional encodings are one thing that like people kind of haven't worked on in a satisfactory way. And I mean, I'm sure there's some nice solution where you just sat down for a few hours, you can figure it out, and it would just make everything way more efficient.
Yeah, I feel like there's to that like Dario's quote. I feel like that also like brings down these rate of innovation by a lot.
Like holding the secrets in.
Yeah.
Yeah, I mean with DeepSeek you saw like they released GRPO and everybody does it in a week.
Right. Exactly. Yeah, I mean, imagine if there were no trade secrets, like how like fucking fast things will go, and like
Yeah.
I just want to see that word one day. Like eventually, everybody knows that within like 20 years, everyone's gonna know it,
Right.
but they will just slow down the whole civilization.
Yeah, it sucks. I'm not a big fan of like intellectual property law in general.
Yeah.
Like you shouldn't be able to copyright anything. I get private property. It's like really hard to build a house, and if somebody just comes and like occupies it, spots and everything,
Yeah.
it's super screwed.
Yeah.
Like it's dangerous for your family. But somebody uses your logo. Like, why is the government stepping in? Man downloads your code and you start crying. Shut up. Does it cost you anything when somebody hits copy paste?
Right.
I don't know. All that stuff's stupid to me.
Yeah. Yeah, I remember like seeing. You remember we did that guys that we watched the video of like NBC. Like he had on his GitHub repo saying like stuff like if you change this code without my permission, then I'm gonna like fuck you. Stuff like that.
That's crazy.
Yeah. Like it's on GitHub, and he had like written all that stuff like licensing shit.
So stupid.
It's not even like great MPC code. Like I think the version that we wrote is like far better than it.
Yeah, usually the really good programmers will open source their stuff, and then it's always like some dumbass engineer who copyrights it and requests that you like ask for permission. It's kind of like a tell that somebody's no good.
Okay, I have one question though.
Sure.
How does the target one is slower than the current one? Like, how do you make sure that that's the case?
Row, that linear interpolation, you did this.
You just okay. Oh yeah. Okay. Yeah. Understand. Okay. Yeah.
It's always going to be slower, but But if rho is equal to 1,
Yeah.
or excuse me, if rho is equal to 0, you're going to go exactly.
The same.
Yeah, it's going to be right on it too.
So the only difference that comes is in the weights updation step. You're kind of like reducing its learning rate than the normal QC.
Yeah, it just lags behind. You can imagine like if you're holding a dog on a leash and it's kind of like tired, then you can run in a direction. You can change direction, but the dog won't move that much.
Or if the dog is too energetic, you're slouchy.
So yeah, if you're standing here and the dog's right there and you're running that way, then for a little while you're not going to get pulled like this at the same speed as him. You're actually going to get pulled in like this, and kind of slow, and you trail on him. Yeah, it's like this path, right? The dog goes this way, and you start here, and you kind of take this path.
And I forgot the bigger picture, the main loop, the main loop that you had that you would run onto convergence.
Yeah.
Is that running like in every iteration? Is that running these update steps?
Yeah. So
Or was there another training loop inside of that big loop?
there were two. So there is every so often you're going to start doing updates. So literally in a single episode, you can learn everything possible and get perfect performance and get the perfect policy function. Eyesight. So you every so often will run an update, and when you run that update, you then do a certain number of updates pre-designed. And then you'll do your you can go compute your targets, right? You'll pick some batches from your replay buffer. You'll compute your target flag. You will update the Q networks in the direction of the target, the entropy add in. You'll then update your policy using the reparametrization trick, and then you'll update the target networks. And that's the loop. And you do that once per episode, per batch.
When you said batch, like they're running in parallel, and you said like
No, there's no parallel. It's save stuff from before, like from the replay buffer.
So how do you find a batch?
You just randomly sample your replay buffer a few times. You can do them in parallel on the update step, but you don't have to. And it's not like you're running multiple episodes. You already have it in your replay buffer. This seems more parallelizable though. Sort of. The update step is parallelizable, but populating the replay buffer is not.
Yeah.
You could actually have like one thread that's playing the game and collecting replay buffer stuff all the time, and then you have like several other threads, like a GPU, doing updates all the time.
Yeah. That's exactly what I was thinking.
Right. So you don't have a condition on when you re-update. You just update as fast as you can all the time as possible.
Yeah, and that's why there's AI quote unquote labs. Like they just keep doing this.
Well, like trying to come up with better ways to design the loops, or is it like making the hardware bigger?
They distribute better.
Yeah. Yep.
Yeah, I want to do that just for like experience of it.
Yeah.
But I would not like to do that for the rest of my life.
Right. Yeah, we get old in like 3 years.
I feel like the GPU programming is such a mess right now.
Yeah.
Do you have something to say about it?
Just use PyTorch.
Use
PyTorch bucket. Don't worry about it. Don't try CUDA. You can if you want to, but go to PyTorch first, and then if you have to, use CUDA. But you don't have to. Don't worry about it. So you can either write CUDA or you can write on Moore's law a little bit and probably Moore's law is going to be faster than your CUDA learning.
Be optimistic. Don't worry about it.
So just go on vacation instead of writing code, and you'll get better performance that way. So stupid. All right. I'm going to kill the recording. And then I'm going to go eat. Is there anything else? That's all of Soft Actor-Critic. It's just like literally just the reparametrization trick we still have to do to figure out. And running it in Lunar Lambda v3. And that's it.
They also have that built in, or
Yeah, I think that's the last thing we got added to Stable Baselines 3. Because everything else after that is Soft Actor-Critic is still state of the art for general neural networks, but they have other algorithms for transformer-based models.
like making these transformer based, or like
So if your neural networks for control, like your policy network, is a transformer, then you have more complicated reinforcement learning algorithms.
these ones do not work well.
They do work. You can still use Soft Actor-Critic. It's just like there are more complicated schemes that you can use that get better performance. Another thing is we haven't talked about any of the stuff like mu0 and alpha0 and Dreamer and Monte Carlo tree search and all this. They're not really viable to use on the rockets because they're expensive. You have to learn, like in mu0, it's nice because you will have, what is it? You got a Q network. So you have a game, like you'll have Go or something, and you'll have a bunch of stones on the board. You know, just a bunch of stuff on the board. And there's 19 by 19 grid, and each one has nothing on it that has a black stone or a white stone. And so you can plug that into a convolutional neural network. So you're good at this kind of grid design. And it's visual.
Yeah.
And so you plug all that into ConvNet. The convolutional neural network feeds into a policy network.
Okay.
And what the policy network does is they train it on professional games. And so it tries to say, what's the likelihood of a professional playing every type of move that could be played in the current state. They also have a value head. The value network. And so it's a V function. And it tries to say, they have two value heads. So one is trying to predict the probability of winning anything in the current state for black. And the other value head is that's a percentage win. And the other value head is a score predictor.
Oh, I see.
Which doesn't matter too much. But just for fun, if you're playing against this AI and you want to see what the score likely will come out to be, it's fun to train that. So these can actually get used. Firstly, what you do is you quickly, as soon as the model mu0 sees the state, it outputs a policy distribution. So it's like, hey, if I got to play in blitz, I'm going to play quick. And then it wants to be able to think. So you have a simulator built in, AlphaZero works this way. You imagine all the actions you can take, all the moves you can make. And maybe you can filter and weight by the policies, but you can also just try everything. And you can do Monte Carlo tree search rollouts, where you imagine taking a move, checking the after state value, and then once you find the best one of those, you can then do further moves, and you can roll out and figure out what the full line of play is going to be. And you can continue to train while you're playing, actually, online.
So Monte Carlo's research works there. But the trouble is, like, you got to program the after state role model so that you can simulate what the game looks like after you plug it back into the value function. So that sucks. So mu0 has this other thing where they have a role model, and what they can do is they can say, take an action, we'll take a state. So that's one input. States can go in. Actually, this comes from the convolutional network. So it can take a state to set the initial conditions of the world. It can also update the state. This is a neural network, by the way. It's not the program. So it can update the state if you flip a switch in it to 1. You just press a button and it updates some next time step. And also, it feeds out to these guys. These no longer come from the CNN. So you're routing everything to the whole model. And the trick is that during training, you try to make this iteration step accurate and act as if you were actually taking the actions. And so it learns the minimal representation of the world, the cheapest, computationally efficient way to predict what's going to happen in the future without actually having to program anything about it. So that is really nice because it works for every possible environment.
That's the paper that you sent me.
mu0, yeah.
Which had like this purple crystal ores on the chess piece.
Yeah.
Yeah.
Yeah, those Google papers are something else.
I gotta go catch the bus.
Okay. I'm about to head out too.
Otherwise, I'm gonna have to like walk my ass back. It was a nice session though.
Yeah, I'm sorry about the reparametrization stuff. I know that took way too long. But so next week's spring break,